All right, let's dive right into this explainer and decode the absolutely fascinating chemistry behind lactose. It's the secret engine driving all your favorite dairy products. When we pour a glass of cold milk or scoop a bowl of ice cream, we rarely stop to think about the microscopic architecture making that whole experience possible. But today, we're going to unpack exactly what milk sugar is, how it's built from the ground up, and why it causes so much brilliant and, let's be honest, sometimes frustrating drama in your kitchen. To kick things off, you might naturally assume that every single mammal relies on this specific sugar to feed their young. I mean, it is the defining carbohydrate of milk across the globe, right? But is that actually a universal rule of nature? Actually, no. What's really interesting here is that nature always has exceptions. Take the California sea lion and the hooded seal, for example. Their milk contains absolutely 0% lactose. Zero. It turns out that while lactose is incredibly common, it isn't a strict requirement for mammalian survival. And honestly, that makes its presence in the rest of the animal kingdom all the more intriguing.
So here's our roadmap for today. First, we'll meet the milk sugar. Then, we'll see why not all milk is equal. After that, we'll peek inside the mammary gland factory, explore the two faces of lactose, and finally, look at the culinary drama in dairy.
Okay, section 1. Meet the milk sugar, the basics of lactose. Let's get down to the fundamentals.
So think of lactose as a tiny molecular structure built from two unique puzzle pieces, perfectly snapped together. In chemistry terms, it's a disaccharide, di just meaning two. Those two foundational pieces are glucose and galactose, and they're linked together by something called a beta-1,4 glycosidic bond. Now that specific bond, that's exactly what lactose-intolerant individuals lack the enzyme to easily break apart. It's a tough little connection. You might be wondering, what's the big deal? Well, the crucial point is that this sugar isn't just about simple sweetness. In fact, lactose is remarkably less sweet than regular table sugar, but its real power lies in its utility. It's the essential food source for the bacteria that give us yogurt and cheese. It literally dictates the smooth texture of your frozen desserts, and it even drives those beautiful browning color and flavor changes when you cook with highly heated milk products. Moving right along to section 2, not all milk is equal. Variation across species and time. There is a really stark contrast in biology when it comes to milk sugar. Check out humans at the top. Human milk is incredibly lactose-rich, sitting way up at 7%. Compare that to standard cow's milk, which hovers around 4.8%. And of course, there's our California sea lion at the bottom with a flat 0. This super high lactose concentration in humans actually helps drive early brain development and provides a massive, easily accessible energy source for infants. But get this, the variation doesn't just happen between different animals, it happens within the exact same animal over time. There's this fascinating inverse relationship. During early lactation, the mother's body prioritizes high lactose production. But as lactation enters the late stages, lactose drops while fat and proteins increase. The milk is essentially shifting its whole nutritional strategy, prioritizing dense energy through fat later on in the feeding cycle. And this shift has profound physical effects because of something called the water drawing effect. Basically, lactose acts as an osmotic balancer. Think of it like a magnet for moisture. Wherever lactose goes, water follows. This means when lactose levels naturally drop during late lactation, or if they drop suddenly due to other health issues like mastitis, the water content also decreases. To keep the fluid balanced, the cow's body actually has to pull in more salts, like chloride, which makes the milk chemically abnormal. All right, section 3, the mammary gland factory, how biology builds sugar. Let's see how the stuff is actually made. The biological assembly line is surprisingly elegant. It takes basic blood sugar and transforms it step by step into unique milk sugar, and it all happens exclusively inside the mammary gland. First, the body pulls raw glucose directly from the bloodstream. Then, a chain reaction called the Lelorg pathway converts some of that glucose into a primed molecule called UDP-galactose. Finally, a master enzyme called lactose synthase acts like a molecular stapler, just snapping the galactose and the remaining glucose right together to form lactose. But here is where the biology gets truly wild. That master enzyme, lactose synthetase, it actually isn't very good at its job on its own. It needs a highly specific key to work efficiently. And when it gets that key, it becomes an astonishing 1,000 times more specific for glucose. 1,000 times. That magic key is a whey protein called alpha-lactalbumin. Without it, The enzyme would just randomly attach galactose to all sorts of other molecules, completely messing up the process. But with alpha-lactalbumin, the factory produces nothing but pure lactose. And this brilliantly illustrates why human milk has such high lactose compared to cows. We naturally have super high levels of this specific controlling alpha-lactalbumin protein. More of this protein simply equals more lactose. Which brings us to section 4, the two faces of lactose, alpha versus beta. Believe it or not, lactose essentially has an alter ego. The only difference between its two faces is the physical direction of a single molecule group, the OH or hydroxyl group. If it points downwards, you get alpha lactose. And alpha lactose is, frankly, a bit of a nightmare. It's less sweet and it has terrible solubility, meaning it turns into stubborn, crunchy little crystals. But if the group points upwards, you get beta lactose. Beta is sweeter, highly soluble, and dissolves fast, making it the absolute preferred form for things like infant formula powders.
Finally, Section 5, Culinary Drama in Dairy, Freezing, Drying, and Cooking. Let's see how this molecular chemistry plays out in the real world.
Take freezing, for example. Have you ever had ice cream that felt weirdly sandy? When you freeze dairy without carefully controlling for lactose, you don't just get ice. You force a destructive chemical reaction. The pure water freezes first. This leaves the lactose trapped in a shrinking pool of unfrozen water until it becomes incredibly supersaturated. That stubborn, low-solubility alpha lactose panics and crystallizes into sharp little shards. These shards draw away even more water, concentrating the milk salts so intensely that the surrounding casein proteins actually collapse and clump together, a process called flocculation. You end up with a ruined, sandy texture. Definitely not what you want. And the exact same drama happens if moisture sneaks into your dried milk powder. When milk is spray-dried properly, the lactose forms a smooth, glass-like state. But if it absorbs even a little humidity from the air, it becomes mobile and immediately starts crystallizing back into that crunchy alpha-lactose form. As the crystals grow, they form physical crevices, creating localized high-salt sounds that, once again, destabilize the proteins. This leads to greeny, separated dairy products that nobody wants to eat. But hey, lactose's behavior isn't always a negative thing. Sometimes it's the very thing that makes our food incredibly delicious. Because lactose is what chemists call a reducing sugar. It contains a free hemiacidyl group. Think of it as an open molecular hand that can easily grab onto other things. When exposed to heat, this open hand eagerly grabs onto the amino acids in milk proteins, specifically lysine. This kicks off the famous Maillard reaction, which ultimately produces those rich, beautiful brown compounds called melanoidins.
Now, while this reaction is exactly what you want when baking pastries or creating certain caramelized sauces, it is a double-edged sword for commercial dairy. Uncontrolled Maillard reactions in milk powders can lead to unwanted browning, strange off-flavors over time, and a distinct loss of nutritional value. That essential amino acid, lysine, literally gets permanently bound up and destroyed by the sugar.
So hopefully, this explainer has shown you that there is a fascinating, highly complex, hidden world of molecular architecture sitting right there in your fridge. From the biological factories and mammalian glands to the delicate balance of alpha and beta crystals dictating the texture of your dessert, lactose is just so much more than a simple sweetener. The next time you enjoy a perfectly smooth scoop of ice cream or the golden brown crust of a baked treat, ask yourself, are you just tasting a recipe, or are you tasting the intricate structural magic of milk sugar?